Hey everyone, this is How to Write a Chess Engine Introduction. This video is mainly to gauge some interest on this topic, see if people want to learn more about this in detail, go through some abstract ideas and eventually getting them into code and actually seeing the output and possibly even having our engines play together. So um, let's see. So to start out, the programming language used, and this is going to be C and C++. This is mainly because we can guarantee performance. We can guarantee that we can eventually extract as much performance as we need to. We have, it's a very low level language, so we can basically do whatever we want, and that's kind of what you need in terms of performance. This engine is mainly to be written from scratch. It is no libraries, no frameworks needed. This is a from scratch type of thing. It sounds like it's going to be a lot of work, but actually engines don't require that much code. It's mostly understanding concepts and ideas and then implementing those, and then turns out that the code's not that bad to write. So um, yeah, you can basically use any language, anything you want to do. It's because we're not using libraries and frameworks, it gives us a lot of freedom in that. Um, and one of the bigger goals of writing a chess engine really is to learn how to write high performance code. Engines are about speed and efficiency. You can write the fastest code on the planet, but if you don't have an efficient algorithm, then it doesn't matter, right? And if you have an efficient algorithm, but you didn't really write the code that well, then it's not going to perform well. So it's about blending these two, thinking about them together. How do you do this? To really extract the performance from the machine, right? Because again, at the end of the day, we're running this on a machine, and we need to write our code such that the algorithm and the code align to what the machine actually is good at. So, the path of writing a chess engine. So, how do you go about this? The first idea in any project is you start simple, right? You can have a big goal and like a big idea, like a chess engine. What is a chess engine? I mean, it basically just has to take in some state and then respond with a move or something like that, right? So we don't need to make like a stockfish from the start, but you do want to eventually get to like those types of levels of performance and accuracy and rating. So um, one thing that's really, really important about writing a chess engine is the correctness. If you write, an engine and it's super fast, but it doesn't work, I mean, no one cares. It's just the end of the day, right? Like these things need to work. They need to we need to make sure that they work, and then after that, we can build speed on top of it, right? So unit tests are a good option for this. We don't have to write a bunch for all like every single function, but it's really good to have tests where you would say, okay, like here's a game, play through the game, and just make sure that those games, those moves were considered legal by the engine, and then maybe throw in a state where it's like, okay, here's a position, and then you say, well, these are the legal moves and these are not the legal moves, and you just check it against the engine, right? So we can do these very high level, easy unit tests. And then also, if you start play testing your engine, you start noticing that it's trying to do moves that aren't legal, then you can simply just recreate that position and then have that test fail and then fix the bug and then test starts working again. So that's kind of how I would drive the unit tests here. Not much at a functional level, but more just at a high level, just to make sure that an engine's performing properly. And another thing to realize is, especially when working on projects, is refactoring is going to happen, right? This is going to happen a lot. You're going to realize that the way you wrote the code sometimes is not the easiest way, or it doesn't allow you to do certain things, or maybe it's not performing enough, and that's fine, right? Rewriting code's not a bad thing. This just means that you're learning and you're iterating. So that is something to expect. And usually, when going through these processes and learning, you should start out with the simple solutions, right? The ones that you think of yourself, or just very basic, and then just keep rewriting the code until it becomes great code. So over the series, a chess engine is really about optimizations. It turns out that when you're writing an engine, it's pretty easy to encode like a pawn moves forward, right? Or on its first move, it can move forward twice, and then it can capture left and right if there's a piece on it of the opposite color. And all these things are very easy to do and easy to encode in an engine. And that's not really where the effort is meant to be spent. The real effort is meant to be spent on optimizations, because when you really think about an engine, most classical engines are basically just searching for moves, right? And it's that searching that takes a long time because, as we know, there's a lot of moves, right? There's tons of moves that can be made. So when we're making our engine, we need to figure out how do we generate moves quickly? How do we evaluate the moves quickly? But also, we kind of don't want to do redundant work, and we want to make sure that the moves that we're generating we actually care about. And if there's ways to say, you know what, let's stop searching in this area and go somewhere else. So there's all these ideas about efficiency of like this large search space, right? There's a lot of total number of positions and a lot of moves. You know, how do we like efficiently traverse all these positions, but also not looking at everything, because looking at everything's going to be way too slow. It's just not going to be possible. So in terms of optimizations, we have some things like bitboards, which is like a board representation. One might start with a 2D array where you store maybe values of pieces, like this is a white pawn and a white knight or white king, and this is a black king, black queen, or something like that. But it turns out that that's not so great. So we have something called bitboards that allow us to perform operations that we care about extremely quickly, right? That's a very good concept, just an algorithm design or code design is you always want the thing you're going to do a lot to be fast. So you design it in such a way. And there's always trade-offs, right? There's no design that's ever going to make every operation perfectly fast. So we choose bitboards because it tends to be that these are operations we want to do and do them fast. Search algorithms, there's something called alpha beta pruning. Effectively, what this is just generate state, explore, and compare what we've already explored with to what we're going to, and then possibly we can maybe prune or not look at certain positions because we know that maybe it's such a bad move there's no point looking at it, right? So if there's a move we know is going to lead to checkmate, it's probably not even or that's going to lead to our own checkmate. There's probably no real reason to look at it anymore. So it's the kind of ideas like that where you can avoid looking at moves that don't really make sense at the moment. And in other words, there's also caching. Caching is a super important concept in just computer science, and in chess engines, it is very important. There's a lot of moves and a lot of representations of things where we kind of don't want to keep recomputing them every single time. And we can cache moves, and there's another idea of magic bitboards, which is a fancy way of saying storing moves for bishops and rooks efficiently. Bishops and rooks, which is also what a queen is. A queen is a bishop and a rook together. These three pieces tend to have different move patterns based on the board, right? A bishop can go up to and including to its opponent's space, or just up to but not including to its own piece color. So um, thinking of it in this way, you can kind of see that the moves that a bishop can do depend on the board state. But something like a knight, the knight doesn't really mind what's on the board. It can just hop over things. It has this nice little L shape. So if I have a knight that's like on e4, it always moves to the same spots. Basically, no matter what, it's always threatening the same spots. But a bishop, depending on what's on its diagonal, it can't go farther, and it's a little bit harder to keep track of that. But there are ways to do it, and that's what a magic bitboard is at the end of the day. That's what the problem that it's solving. So these are just some ideas of optimizations that we'll go through the series. So going forward, I just want to get some general interest on this topic. Do you want to learn about these things? Are these things that people are looking to understand? The real big goal of this is really to understand how do you write performant code? How do you look at this problem and then really think outside the box and understand these concepts such that you can write a nice fast algorithm, fast chess engine. So yeah, please let me know